The interstellar medium, ISM, is the matter and radiation that exists in the space between star systems within a galaxy. Despite its name suggesting emptiness, interstellar space is filled with a complex mixture of gas in various forms: ionic, atomic, and molecular, dust particles, cosmic rays, and an interstellar radiation field. This medium, though extraordinarily tenuous by terrestrial standards, plays a crucial role in the evolution of galaxies and the formation of new stars. The ISM is characterized by a wide range of physical conditions, with temperatures spanning from a frigid 10 Kelvin to a scorching 8,000 Kelvin or higher, and densities varying from as low as 100 ions per cubic meter in hot regions to as high as 10-12 molecules per cubic meter in dense molecular clouds. This remarkable diversity in physical conditions gives rise to distinct phases within the ISM, each with its own unique properties and significance in the cosmic ecosystem. Understanding the temperature and density distribution of the ISM is fundamental to comprehending the processes that shape our galaxy and drive its evolution over cosmic timescales. The interstellar medium consists predominantly of gas, with dust making up only about 1% by mass. The gas component is primarily hydrogen, 70% by mass, with helium constituting approximately 28% and heavier elements, known as metals in astronomical terminology, making up the remaining 1.5%. When measured by the number of atoms rather than by mass, hydrogen dominates even more strongly, accounting for 91% of all atoms in the ISM, while helium represents 8.9% and heavier elements only 0.1%. The hydrogen and helium in the ISM are largely primordial, created during the first minutes after the Big Bang through the process of primordial nucleosynthesis. In contrast, the heavier elements have been synthesized through nuclear fusion in stellar interiors and dispersed into the ISM through stellar winds and explosive events like novae and supernovae. This process of stellar nucleosynthesis continuously enriches the ISM with metals, gradually increasing their abundance over cosmic time and providing essential elements for the formation of planets and ultimately life. The gas in the ISM exists in multiple states: molecular, where atoms combine to form molecules, most commonly H2; atomic, neutral hydrogen and helium atoms; and ionized, where electrons have been stripped from atoms, creating a plasma. The predominant state of gas in a particular region depends on local conditions, especially temperature and the intensity of the local radiation field. Beyond the gaseous component, interstellar dust consists of tiny solid particles, typically 0.1 to 1 micrometer in size, composed primarily of silicates, carbon compounds, and ice mantles in colder regions. Despite its minor contribution to the total mass, dust plays critical roles in interstellar chemistry, acting as a catalyst for molecular formation and in regulating the thermal balance of the ISM by absorbing and re-radiating energy. The interstellar medium exhibits a multi-phase structure, with each phase characterized by different temperatures, densities, and ionization states. This structure arises from the complex interplay between various heating and cooling processes operating in interstellar space. The concept of thermal phases in the ISM was pioneered by theoretical studies that demonstrated how the interaction between heating and cooling mechanisms could naturally lead to distinct stable phases in pressure equilibrium with one another. In particular, the shape of the cooling curve, the relationship between cooling rate and temperature, combined with various heating processes, creates conditions where gas at certain temperatures cools rapidly, while at other temperatures, it can remain stable for extended periods. The onset of a new stable phase typically reflects either the emergence of a new cooling mechanism or the decline of a heating source. For instance, cold HI clouds form due to the increased importance of cooling at higher densities, while the warm intercloud medium results from Lya and 6300 Oro cooling at higher temperatures. The hot phase of the ISM primarily reflects the recent input of supernova energy, while cold molecular clouds form as a result of increased cooling from rotational transitions in molecules. However, molecular clouds somewhat defy this simple classification scheme, as their existence also reflects the importance of self-gravity in their formation and maintenance. While thermal pressure contributes to the equilibrium between phases, it is important to note that magnetic fields and turbulent motions typically provide more significant pressure support in the ISM than thermal pressure alone. This additional pressure from non-thermal sources plays a crucial role in stabilizing the multi-phase structure and preventing rapid collapse of denser regions. The various phases of the ISM are not isolated from one another, but are interconnected through complex dynamics, with material cycling between phases over time due to heating, cooling, compression, and expansion, driven by stellar feedback and galactic dynamics. The cold neutral medium, CNM, represents one of the fundamental phases of the interstellar medium, characterized by relatively low temperatures and higher densities compared to other neutral phases. Typically, the CNM has temperatures of 300 K, with a high particle density ranging from approximately 10 to 100 cm3. This cold gas exists primarily in the form of neutral atomic hydrogen and can be observed through its 21 cm absorption features against background radio sources. The CNM is not distributed uniformly throughout the galaxy, but tends to form discrete clouds or filaments embedded within the more pervasive warm phases of the ISM. The formation of the CNM appears to be contingent on reaching a threshold column density, below which it becomes difficult to form significant amounts of cold gas. Research has identified a threshold hydrogen column density of approximately 2 x 1020 cm2 for the formation of the CNM in the galactic ISM. This threshold exists because at lower column densities, the gas cannot effectively shield itself against background heating radiation, preventing it from cooling to CNM temperatures. Sightlines with column densities exceeding this threshold typically show much lower spin temperatures, with a median of around 350 K, indicating a substantial presence of cold gas. The existence of this threshold explains why the CNM fraction increases with increasing HI column density. Higher column densities provide more effective self-shielding against ionizing radiation, creating favorable conditions for CNM formation. Observationally, the CNM can be studied through the combination of 21 cm emission and absorption measurements, which allow astronomers to determine both the column density and spin temperature of the gas. The spin temperature is a measure of the relative population of the two hyperfine levels of the ground state of neutral hydrogen and serves as an indicator of the physical temperature of the gas. In regions where the CNM dominates, the measured spin temperatures are typically lower, reflecting the cooler nature of this phase. The cooling of the CNM is primarily facilitated by fine structure line emission from singly ionized carbon, which becomes increasingly efficient at the higher densities characteristic of this phase. The warm neutral medium, WNM, constitutes a significant component of the interstellar medium, characterized by considerably higher temperatures and lower densities than the CNM. Typical WNM temperatures range from approximately 5,000 K to 8,000 K, with particle densities between roughly 0.1 and 1 cm3. This phase consists primarily of neutral atomic hydrogen and occupies a much larger volume of the galactic disk compared to the CNM, effectively serving as the intercloud medium in which colder, denser structures are embedded. The WNM is maintained at its elevated temperature primarily by photoelectric heating from dust grains exposed to ultraviolet radiation, as well as by cosmic ray heating. Observational studies of the WNM present significant challenges due to its low density and high temperature, which result in weak absorption features. Sensitive radio observations with instruments like the Westerbork Synthesis Radio Telescope have achieved optical depth sensitivities of approximately 1 to 2 x 10 to 3, essential for detecting the weak absorption signatures of the WNM. These observations have revealed that approximately 50% of observed sightlines have average spin temperatures exceeding 500 K, indicating WNM dominance in these directions. In particular, sightlines with hydrogen column densities below the threshold value of 2 x 1020 cm2 consistently show high spin temperatures, with a median of approximately 2000 K, suggesting that these regions consist almost entirely of WNM. The WNM plays a crucial role in the overall ecology of the interstellar medium, serving as a reservoir of potential star-forming material that can transition to colder phases under appropriate conditions. The cooling of the WNM is primarily accomplished through Lya emission for temperatures above about 8,000 K, and fine structure line emission from neutral oxygen at somewhat lower temperatures. However, these cooling mechanisms become less efficient at the densities typical of the WNM, allowing this phase to maintain its elevated temperature in thermal equilibrium. The balance between the WNM and CNM phases is determined not only by thermal processes, but also by dynamical effects such as turbulence and shocks, which can drive transitions between these phases by compressing or rarefying the gas. The molecular phase represents the coldest and densest component of the interstellar medium, with temperatures as low as 10 Kelvin and densities that can reach 1012 molecules per cubic meter, equivalent to 106 molecules per cubic centimeter, or even higher in the cores of dense clouds. This phase is composed predominantly of molecular hydrogen, H2, which forms on the surfaces of dust grains, where atoms can meet and combine while releasing binding energy. Once formed, molecular clouds are self-shielding against dissociating radiation, allowing them to maintain their molecular nature despite the presence of the interstellar radiation field. In addition to H2, a rich variety of other molecules have been detected in these clouds, from simple species like carbon monoxide, CO, to complex organic compounds. Molecular clouds exhibit a hierarchical structure, with diffuse molecular gas gradually increasing in density toward filaments, clumps, and eventually dense cores where star formation can occur. This structure is shaped by a combination of turbulence, magnetic fields, and self-gravity, resulting in a complex morphology spanning multiple spatial scales. The cooling of molecular gas occurs primarily through rotational transitions in molecules, especially CO, which efficiently radiates away thermal energy at low temperatures. This enhanced cooling capability is what allows molecular clouds to reach much lower temperatures than other phases of the ISM. The molecular phase, while comprising only a small fraction of the ISM by volume, contains a substantial portion of the total mass of interstellar material in the galactic disk. These molecular reservoirs are the sites of all known star formation in the galaxy, making them critical components in galactic evolution. The transition from atomic to molecular gas represents a fundamental threshold in the density evolution of the ISM, occurring when densities become sufficient for efficient molecule formation and self-shielding. Observations suggest that this transition typically begins at hydrogen column densities of approximately 2^3x 1020 cm², similar to the threshold for CNM formation, highlighting the interconnected nature of phase transitions in the ISM. The hot ionized medium, Chi-M, constitutes one of the most extreme phases of the interstellar medium, characterized by very high temperatures exceeding 105 K and extending up to 107 K, coupled with exceptionally low densities of approximately 10^2 to 10^3 cm². This phase forms primarily as a result of violent supernova explosions, which inject enormous amounts of energy into the surrounding medium, creating expanding bubbles of hot, ionized gas. These supernova-driven bubbles can grow and merge to form larger structures such as superbubbles and chimneys that may even break through the galactic disk to connect with the galactic halo. The extremely high temperatures of the HM ensure that hydrogen and helium are fully ionized, and even heavier elements are stripped of multiple electrons. At these temperatures, the gas cools primarily through Bremsstrahlung, free emission, and line emission from highly ionized species such as oxygen, nitrogen, and carbon. However, due to the very low density of this phase, cooling is inefficient, allowing the hot gas to persist for extended periods, potentially millions of years. This slow cooling rate means that the HM can occupy a significant fraction of the interstellar volume, particularly in the galactic halo, and in regions that have experienced recent supernova activity. Observationally, the HM manifests itself through soft X-ray emission and highly ionized ultraviolet absorption lines from species such as OVIs, NV, and CF. These observations have revealed that the SHIEM is not distributed uniformly, but forms a complex network of tunnels, bubbles, and cavities throughout the galactic disk and halo. Our own solar system appears to be located within such a structure, known as the local bubble, a region of hot, low-density gas extending several hundred parsecs that was likely created by multiple supernovae in the relatively recent past. The HIM plays a crucial role in the transport of energy and metals throughout the galaxy, and may significantly influence the dynamics of the other phases through its high pressure and the shocks it generates. The warm ionized medium, WIM, represents another significant ionized phase of the ISM, with physical conditions intermediate between the WNM and the HIM. The WIM typically exhibits temperatures of approximately 8,000 to 1,000 K and densities around 0.1 to 0.3 cm3. Unlike the HIM, which is heated by shock waves from supernovae, the WIM is primarily ionized by ultraviolet radiation from hot, massive O and B-type stars. This radiation is energetic enough to ionize hydrogen, but does not heat the gas to the extreme temperatures seen in the HIM. The WIM is also known as the Reynolds layer, or the diffuse ionized gas, DIG. The distribution of the WIM in the galaxy is not uniform, but tends to be concentrated around regions of recent star formation, where ionizing sources are abundant. However, ionized gas is also observed at significant distances from obvious ionizing sources, including at considerable heights above the galactic plane. This suggests that ionizing radiation from OB stars must be able to travel large distances through the ISM, possibly through low-density channels, or chimneys created by clustered supernovae. The WIM has a substantial filling factor in the galaxy, occupying perhaps 20–30% of the volume of the galactic disk, and extending into a thick layer with a scale height of about 1,000 parsecs above and below the plane. Observationally, the WIM is primarily studied through optical emission lines, particularly HA emission from hydrogen recombination, as well as forbidden lines from singly and doubly ionized species such as S2, N2, and O3. These observations reveal that the WIM tends to have a filamentary structure, often associated with large-scale features such as superbubbles and galactic fountains. The WIM represents an important component in the cycling of material between different phases of the ISM, as it can form from the photoionization of neutral gas and eventually recombine to replenish the neutral phases when the ionizing radiation field weakens or the gas moves away from ionizing sources. Theoretical models of the interstellar medium predict that gas should primarily exist in the stable CNM and WNM phases, with minimal material at intermediate temperatures, approximately 500–5,000 K, where cooling and heating rates would drive the gas rapidly toward one of the stable phases. However, observational evidence increasingly suggests that a significant fraction of the ISM may exist in this theoretically unstable temperature range. Sensitive atomic hydrogen observations have detected gas with spin temperatures between about 500 K and 5,000 K, which corresponds to the thermally unstable regime. This unexpected finding challenges simple two-phase models of the ISM and points to the importance of non-equilibrium processes in shaping the temperature distribution of interstellar gas. Several mechanisms have been proposed to explain the presence of gas in the unstable temperature range. Numerical simulations suggest that turbulent flows in the ISM can produce substantial quantities of unstable gas through compression and rarefaction. Studies have shown that turbulent flow collisions could generate up to 30% intermediate temperature gas, while superbubble-driven turbulence might create 8 to 10% unstable gas. Additionally, the typical supernova rate in galaxies can significantly influence the phase balance through shock propagation and the induction of turbulence, continuously pushing stable gas into unstable temperature regimes faster than thermal processes can return it to equilibrium. The observed median fraction of gas in the unstable phase is approximately 0.12%, based on analysis of the spin temperature distribution along multiple quasar sightlines. This substantial proportion of unstable gas underscores the dynamic, non-equilibrium nature of the interstellar medium. Rather than viewing the ISM as a static system of discrete phases in pressure equilibrium, modern understanding emphasizes its nature as a dynamically evolving medium, where thermal phases represent attractors in temperature density space, rather than rigid categories. The ongoing interchange between stable and unstable phases reflects the complex interplay between thermal processes, turbulence, and stellar feedback that characterizes the ISM. The spatial distribution of the different phases of the ISM across the galaxy reveals complex patterns that reflect the underlying physical processes shaping interstellar material. On large scales, the distribution follows the general structure of the galactic disk, with concentration towards spiral arms and a gradual decrease in density, with increasing galactocentric radius and distance from the galactic plane. However, within this broad pattern, there exists considerable small-scale structure, with each phase exhibiting characteristic spatial arrangements. The CNM tends to form discrete clouds and filaments, often aligned with the local magnetic field, while the WNM fills much of the volume between these colder structures. Molecular gas is even more highly structured, forming complexes that are further organized into networks of filaments, clumps, and cores. The vertical distribution of the ISM reveals a distinct stratification of phases. The molecular gas is most tightly confined to the galactic midplane, with a scale height of only about 75 to 150 parsecs, reflecting its relatively high density and efficient cooling. The CNM has a somewhat larger scale height of approximately 100 to 300 parsecs, while the WNM extends much further to around 400–1,000 parsecs. The ionized phases show even greater vertical extension, with the WIM reaching heights of 1,000–2,000 parsecs, and the HIM potentially extending throughout the galactic halo to heights of several kiloparsecs. This stratification results from a combination of factors, including the balance between gravity and pressure support, the distribution of heating sources, and dynamical processes that transport material perpendicular to the galactic plane. Our solar system resides within a particular local environment known as the local bubble or local cavity, a region of hot, low-density gas approximately 150–200 parsecs in diameter. This structure was likely created by multiple supernovae in nearby stellar associations within the past 10 to 20 million years. The local bubble contains very little cold neutral gas and is instead filled primarily with warm and hot ionized material. At the edges of this bubble, where the gas transitions to higher densities, there are regions of neutral and molecular gas, including several small molecular clouds within about 150 parsecs of the Sun. This local structure illustrates how stellar feedback can significantly modify the distribution of ISM phases on scales relevant to individual star systems. The interstellar medium is not a static entity, but undergoes continuous evolution driven by a variety of processes operating across different time scales. The most dramatic changes occur in response to stellar feedback, particularly from massive stars. During their lifetimes, these stars generate strong stellar winds that create bubbles of hot gas, and when they expire in supernova explosions, they inject enormous amounts of energy and newly synthesized elements into the surrounding medium. These energetic events drive shocks that compress nearby gas, potentially triggering phase transitions from WNM to CNM, or even initiating the formation of molecular clouds. Simultaneously, the heating from these events can evaporate existing cold clouds, returning the material to warmer phases. On longer timescales, the cycling of material between different phases follows patterns influenced by galactic dynamics. Gas in spiral arms experiences compression that promotes the formation of molecular clouds and subsequent star formation. As this material moves out of the spiral potential, feedback from the newly formed stars disperses much of the molecular gas back into atomic phases. Over galactic rotation periods, material may cycle multiple times between diffuse and dense phases. Additionally, material exchanges between the disk and halo through galactic fountains, where hot gas rises into the halo, cools, and rains back down onto the disk, further contributing to the dynamical nature of the ISM. Turbulence plays a fundamental role in this temporal evolution, affecting the density and temperature distribution at all scales. Interstellar turbulence is driven by a combination of processes, including supernova explosions, stellar winds, galactic rotation, and gravitational instabilities. This turbulence creates a continuous spectrum of density fluctuations, temporarily pushing gas into unstable temperature regimes and creating transient structures across a wide range of scales. The characteristic velocities of this turbulent motion typically exceed the sound speed in the colder phases of the ISM, making it supersonic and highly compressive, which contributes to the formation of dense regions that may eventually become sites of star formation. The interstellar medium exhibits a remarkable range of temperatures and densities, spanning several orders of magnitude from the cold, dense cores of molecular clouds to the hot, tenuous plasma heated by supernova explosions. This diversity gives rise to a multi-phase structure where distinct regimes of temperature and density coexist in approximate pressure equilibrium. The classic two-phase model of cold and warm neutral media has been expanded to incorporate additional phases, including molecular gas, warm ionized medium, and hot ionized medium, each with characteristic physical conditions and spatial distributions. However, the boundaries between these phases are not sharp, but rather represent transitions in a continuous distribution of temperature and density. The observed temperature and density distribution reflects the complex interplay between various heating and cooling processes, as well as dynamical effects from turbulence, magnetic fields, and stellar feedback. While thermal equilibrium considerations explain the existence of stable phases at certain temperature ranges, non-equilibrium processes appear to maintain a significant fraction of gas in theoretically unstable temperature regimes. This highlights the fundamentally dynamic nature of the ISM, where material continuously cycles between different phases in response to energy input from stars and the dissipation of that energy through cooling processes. Understanding the temperature and density distribution of the ISM is crucial for comprehending galactic evolution and star formation. The conditions in different phases determine where and when new stars can form, which in turn influences the future evolution of the ISM through stellar feedback. This creates a self-regulating system that maintains a balance between different phases while allowing for ongoing star formation. Many questions remain about the detailed physics of phase transitions, the role of magnetic fields and turbulence in shaping the ISM structure, and the precise mechanisms by which stellar feedback regulates the temperature and density distribution across galactic scales. Future observations with increasingly sensitive instruments across the electromagnetic spectrum, combined with advanced numerical simulations, promise to further refine our understanding of this complex and dynamic component of our galaxy.